Okay. Okay, good morning. My name is Ray Zhu. So condensed matter in rice has two components. One is a theory, the other is experiment. So we have these four experimentalists in the Department of Physics, and also we have John Kono, who is a professor in electrical engineering, but also his area include condensed matter physics. We have officially we have three series working on the condensed matter series. So I'm going to introduce them in detail later on. So what is condensed matter? Condensed matter is basically you study a collection of many electrons or many other atoms, and then in a solid state or other forms. Okay, so it's the interface between quantum mechanics, statistical mechanics, and also in the condensed matter, we are concerned about if you have so many electrons, whether you can have totally different phenomena which cannot be deduced from single electrons. So second part, sometimes we call emergent phenomena, or sometimes we call correlated electronic behavior. Okay. So basically, our group all concerned about many electrons, and in terms of the number of atoms, typically 10 to the 20, 10, 21, 23. So let me just go to the first group, Middleton's group. Basically, he focused on experimental nanostructures. So some example including molecular and atomic scale devices. So for instance, he can make transistors out of single molecules. Basically, he can fabricate so-called quantum point contact and then select or some contact which contain single molecules from chemical doping. Okay. So for instance, one of the experiments is to measure noise. In the quantum mechanics, if the structure is very small, noise actually is the signal. Okay. So for instance, if we measure the conductivity versus time, you can see the conductivity actually fluctuates, and in some particular point, the conductivity drops to zero. Okay. Then at this particular point, he measures what's the noise spectrum. You can find that there are different characteristics in terms of the spectrum of noise. For instance, if it goes to this point, basically you don't get any noise. And here you have a noise which contains different frequencies, and different frequencies has different intensity. Okay, so from this, one can deduce back what's going on in terms of the molecular structures. Okay. So second type is working on organic semiconductor. Organic semiconductor can be used for instance, spin injection and other purpose that traditionally people study this in metal, but now similar phenomena can be studied in organic semiconductors, such as polymers. Okay. So number three is strongly correlated nanostructures. We mentioned if you have many electrons, then the behavior of the system depends on how the electrons interacting with each other. So one of the examples is certain oxide and a magnet actually shows very interesting magnetic properties due to the electron-electron correlation. For instance, here, if you make device, if you sweep the bias of the device, the behavior of the current will totally depend on the history of how do you sweep. So that's called hysteresis. So from this hysteresis, one can understand some of the properties in the system. Okay. So the next one is my group. What I'm interested in is, in general speaking, called quantum transport. Okay, just want to understand how electrons move and how the property of the electronic system can be studied by measuring conductivity or resistivity. Okay. So in particular, I'm working on quantum spin, quantum Hall effect, either fractional quantum Hall or integer quantum Hall effect. So first thing is that we want to cool down electron to extremely low temperature in order to study those low energy properties. Okay. So we have one of the lowest temperature apparatus in the whole world for cooling electron. Okay. We can cool down electron to sub-millikelvin, which is less than 1 millikelvin. Okay. So if you measure this temperature in terms of Fermi energy, this is actually the very, very low energy, very, very low temperature. Okay. So one of the things I'm interested in, not only by measuring the electrical conductivity, I also want to study the thermal conductivity. Okay. In the very low temperature in this system, thermal conductivity also quantized. So you don't have continuous or arbitrary unit of conductivity. Rather, you have a unit of a mode, which accounts for this. Okay. So I'm one of the data which is shown here is a measure 10 millikelvin, and you can see a particular interesting state which is called phi-half state, which is a theoretically proposed for quantum computation, and this quantum computation will be topologically protected, so you can have a new system which does not rely on the environment. So number 3 is